me immagino che non avrà. Okay, here we are.
Okay, so, bueno, buenos días a todos. So, good morning. So today we have a seminar entitled Diagnosing Frontal Dynamics from Observations Using a Variational Approach that will be given by Eugenio Cutolo, who, as you know, he's a PhD student on his second year here at IMEDEA. And so the work that he's going to present is part of a paper that he's almost ready to submit. And in the frame of the CALYPSO project funded by the Office of Naval Research, and also the PRISWAT project in the frame of the Space Research Agency. And so it's a collaboration with many co-authors from here in Medea, but also from many colleagues from the US. So you can start, Jenny.
Yes.
Thank you.
Okay, just let me.
And well,
you see it. You see it good?
Yes.
Okay. So, everyone, thanks for being wherever you are, but you're online. And as Fernanda said, this is a seminar for my PhD, presenting the work that I've been doing in this years of PhD. And the title is Diagnosing Frontal Dynamics from Observation Using a Variational Approach. And I take the chance to say thanks to all the co-authors that you see listed down there. And let's start with introduction of some concept, particularly the one of fronts. I'm gonna talk about fronts, and in general, in oceanography, we are interested in fronts for just to list 3 reasons. Probably there are even more, but first of all, it's an observational challenge because I've been putting in the plot on the right, you can see an example of fronts of different variables from a model. So the observational challenge can be somehow represented from this salinity plot that you see in the top panel, because you have a really strong gradient in a small area. So this from an observational point of view is quite challenging, and it's still pretty unresolved. We mostly rely on models even for that, because it's really hard to measure these gradients. And more in general, they are a spot for biological activity. And we can you can see, for example, the tracer in the middle plot, where the red means that a small concentration of this tracer, and the green-blue represent a stronger concentration of tracer. And this is because fronts moves tracer. I'm speaking about tracer, but just to be more specific, in a real world, it means carbon dioxide or even nutrients for fisheries. And the fronts moves this from the surface to the interior thanks to the strong vertical velocity. And as you can see the last plot in the bottom, strong vertical velocity, the positive are the red one and the negative are the blue one, with up to 40 meters per day. So it's, even if it looks like not strong for the vertical motion, those velocities are quite strong. So the fronts are part of these features that enters in what we call submesoscale. And these scales, you can see in the right plot, summary of all the scales involved in oceanography, with all the phenomena, with their spatial and temporal scales. And the submesoscale, I titled this problem because submesoscale is quite overlapped, as you can see in this plot, with other phenomena like tides, inertial motion, and other small scale phenomena. And the submesoscale in general, we refer to submesoscale in general when the Rossby number, that is the ratio between the vorticity and the planetary vorticity, is closer to 1. Instead, the other situation that we control a little, we understand a little bit better, even thanks to the altimeters that we have, data from altimeter that we have, is the mesoscale. And this is instead is when the Rossby number is much smaller. And in general, we can also characterize those dynamics from the vertical velocity. So the mesoscale have small vertical velocity, and instead, as we said in the previous slide, we have much stronger vertical velocity in some mesoscale region. And that's trying to understand what's going on in this small feature. It's one of the aim of the CALYPSO project. With some fantasy, you can understand that it's an acronym, and it means coherent Lagrangian pathways from the surface ocean to the interior. And so the idea is to diagnose the 3D pathways using a physical relation, primitive equation, models, some dynamics that I'm gonna discuss it later, and then compare this the studies with real, with direct Lagrangian measures that are possible to thanks to instruments that are right now in development, Lagrangian float. But more in general, the CALYPSO project right now relies on experiments that have been done in the past years, and in particular, they have been done in the Alboran Sea that you can see in the map here on the top. It's a pretty interesting scenario because it's where the Atlantic water that enters in the Strait of Gibraltar eats somehow with the Mediterranean water, and so there is almost a permanent front between these two water masses. And so we've been doing a really complete sampling with different instruments, so CTD, thrusters, the floats, gliders, even moorings. And the rest of the approach of these experiments even involves models. So we have the WMAP from SOSIB, the PSOM, that it's a process studies from WUI, and even from MIT we have another model. So there are a lot of efforts even in the model in the modeling part. And regarding the theory, yeah, there are these two frameworks, Quasi-Geostrophy and Semi-Geostrophy, that I'm gonna discuss in the next slides. In general, it's okay, nothing more. There is a further experiment planned for 2022, and it's always a collaboration between the US and Spain. Now, getting a little bit more closer to the data that I've been analyzing in my work, let me describe the cruise scenario of the 2019. And in particular, okay, you can see the transect that we have been doing. And you can see in the bathymetry map, that is this biggest one, the transect that we've been doing with the bathymetry. And you can see that we've been sampling an anticyclonic eddy. You can see in the C panel, the SLA, the altimetry with the geostrophic velocity. So there is an anticyclonic circulation. But even more interesting, you can see that in the eastern side of this eddy, there is a front. So this is what I'm going to talk about. And the radius of this eddy is 20 kilometers, as you see. Okay, the data. Okay, if you have in mind the transect that you have been seeing in the map in the previous slide. Now in this map, I'm not using latitude and longitude, but instead kilometers, and so the coordinates are rotated. And you can see in the color the observation day. So we've been sampling this eddy in more or less 2.5 days. You can see also some other points more than the ship transect that are the drifters, since, as I said, in this campaign we have been deploying a lot of drifters, and so some of them crossed pass into the domain into the study area even after we leave the area. So it's interesting that they gives us an idea of the synopticity of the features. And if you focus on the two red boxes, B and C, they are represented the salinity data from that we've been collecting are on the right plot, the corresponding right plots. So you can see that it's a salinity-based front, and it's not totally parallel to the north-south axis, so it's a little bit inclined. And this is interesting because when we want to reconstruct the field, it's quite complex. Okay, this salinity sampling and even the temperature and general the hydrographic data come from underway CTD, that is basically a CTD that is spoiled in the bottom of a boat, of a ship, and we let it free fall, and then we collect on board with a winch. And in our case, our target depth of measurement was around 200 meters depth, and based on the ship speed that we've been following, we obtain a horizontal resolution of more or less 1 kilometers. And so this is giving us the hydrographic information, and instead the information more regarding the shape, and in particular the horizontal velocity, comes from the acoustic, the ADCP. It's a pretty known instrument that, thanks to the Doppler effect, estimate the currents down the boat. So you can see some parameters here that we've been using to configure it. We've been sampling with the software of the builder and WEM-DAS, and instead the post-processing was made using CODAS, a software from the University of Hawaii. And maybe the most important, maybe different compared to other studies, parameters is the percent good, that it means the percentage of observation, the percent, how, let me think how I explain it. Basically, usually the studies on ADCP rely on the 65% of the observation. Instead, we try to, we have been a little bit more strict. It means we remove more bad observation of the ADCP, since the error of the ADCP is going to propagate in our analysis for the method that we have been using. Okay, so an auxiliary data set is made from the dristers. Auxiliary because we've been using mostly for assessment. They didn't enter in the analysis. And the dristers that pass in my area are 3 different types. You can see from the images how they differ. The most important characteristic probably is the drop depth. That's changed from the 50 meters of the SSVP to the 0.3 of the CART and the 0.5 of the WDVOS. And so after this summary of all the data, I want to highlight the problems that we faced before starting with the methods. So even if our sampling was quite dense, especially along the transect, we still have gaps in our sampling, and this is a common problem. We can't be everywhere with all the instruments. We don't have unlimited budget, unfortunately. So this is a problem at the moment of reconstructing the fields, because we can have wrong gradients in the area where we don't have samples. So this is one of the problems, and somehow it's also connected to the second one, that it's, since we are interested in vertical velocity, we don't have a direct measurements of the vertical velocity, or at least even if these instruments that you see in the picture, it's under development, that it's Lagrangian float from Eric Dassaro. It is gonna measure the vertical velocity in theory, but just in a point. So if we are interested in the pattern, this is not yet possible, or at least quite challenging. So we have these 2 problems. Let's see how we deal with them in the method parts. So first of all, I'm gonna present you the variational analysis. That it's an approach to map a field from our sparse observation, and it does this just minimizing a cost function, and usually the cost function involves the deviation from our observation, and also a smoothing term. But it's the nice things of this approach that this basic cost function can be extended with further terms, and this is actually what I've been doing. And using the thermal wind equation that connects the velocity with density gradients, I've been developing a constraint that use the ADCP information to improves the density reconstruction of the UCTD data. What it's doing in the constraint is basically somehow increasing the correlation length in the flow direction, but it's doing this in a physical sense, like with a physical equation, not in a statistical manner. Okay, so once we have the reconstruction of the hydrography, we still need to know the vertical velocity, and to obtain the vertical velocity, we rely on a pretty known omega equation. One is developed by Joskin in 1978, and it relies on the Quasi-Geostrophy approach, and that approximates the Navier-Stokes equation. And in its Q-vector representation, it's shown there in the equation. Maybe the most important concept here that we can, if you see the terms involved in the equation, that we can estimate omega, the vertical velocity, just knowing the density and the geostrophic velocity that also can be computed from the density once we select a reference level. So this approach, the limitation of this approach is that should be used in an area where the Rossby number is quite small, so less than 1, smaller than 1. But we also been using another approach. The equation is similar, but you have to make a coordinate change. And then this equation should be a little bit better than the Quasi-Geostrophy one for the area where the Rossby number is closer to 1, and in particular, according to this article, should be better in a not strongly curved front like the one that we have been sampling. So 2 omega equation to estimate the vertical velocity, and a further method that is based on a work of Marafredich of the 2019, where we use the divergent component of the horizontal velocity of the ADCP mapped on a constant density surface. And then what we do is simply project this divergent velocity to the isopycnal slope, because you can imagine that an isopycnal, a constant density surface, has different depths. So if the divergent velocity goes in the direction of where the isopycnal is going down, we have downwelling, negative along-isopycnal vertical velocity. So this is a further estimation of the vertical velocity. Okay, just to have an overview, I know the methods are quite maybe complex, but to summarize, we've been using the UCTD and the ADCP data. The UCTD data have been also optimally interpolated to have a reference for the other methods. And then we've been doing the univariate analysis with the basic cost function of that I saw when I talk about the variational analysis. And then I've been doing also a multivariate analysis with the constraint that connect the ADCP and the UCTD. And okay, maybe I'm gonna talk about this in the next slide, but the ADCP velocity have been decomposed in the 2 components, the rotational and the divergent one. The rotational was used for the constraint, and instead the divergent for the along-isopycnal vertical velocity estimation that I've been talking in the previous slide. So let's start with some results. And let's start with the ADCP. As I said just a moment ago, we've been, okay, first of all, you can see in the right plot, the difference between the raw data of the ADCP and the interpolation. It works quite good. And this is just a transect, for example. And then in the map on the left, you can see the red arrows are the divergent component of the horizontal velocity, and they are toward the epicenter. This is pretty interesting and will be used later. Instead, the rotational component are present the same shape of the eddy, basically. And this has been obtained, as I said, with the Helmholtz decomposition. Then we can compare this ADCP velocity that the same plot is one here, the one in the top left panel, and compare this velocity, the rotational velocity of the ADCP, with the geostrophic horizontal velocity from our reconstruction method. So we have the top right, that is the one from the UCDD univariate analysis, that presents quite strong magnitude and even a lot of meanders. That's probably because even if the gradients are preserved in this variational approach, maybe the lack of data between the transect generate artifacts and meanders. Instead, the OI, that is this one, the bottom left, it's presenting much smoother field, but even the magnitude, it's really weaker and not comparable with the one of the ADCP. The best one looks like the VUO, that is the multivariate analysis. And maybe, okay, so, and you can see how even the magnitude is quite according to the ADCP. Okay, and then in this plot on the right, you can see just to have an idea of our reference level, that was 200 meters depth, and the level of no motion, sorry, not reference level. Okay, so even if we have described a little bit the difference between our velocity field, we want to quantify a little bit better the difference and how we improve the horizontal velocity in a different reconstruction. So to design, we've been using a skill score defined by Liu et al. In 2011. You can see the definition formula in the left. But basically, the idea is to compare the real drifter trajectories with virtual drifter advected using the velocity field that we want to compare. And then the skill score is normalized, so it's gonna be equal to 1 when there is a good agreement between a real drifter and virtual particles, and instead 0 when there is a bad agreement. And you actually have an example of what the different methods compared with the real drifter. So the real is the blue one, and then you have the best advection was obtained with the multivariate analysis, actually. Okay, so this skill score allows to make a better assessment of our reconstruction. In particular, you can see in the histogram on the left, the skill score averaged for the area of same presenting a similar presenting the same range of ADCP velocity magnitude, because our idea in the end is that the multivariate analysis is improving, is the best reconstruction, but we suspect that the improvements are limited to the area where there is a strong signal of the ADCP. And it's actually what we have been observing, seeing these 50% improvements in the area where the ADCP velocity are stronger. In the map here, you can see the difference in percentage between the skill score of the multivariate analysis and the OI, the optimal interpolation. So you see the red dots represents when the multivariate analysis improves the reconstruction, the skill score, and all these points are in the area of stronger strong or horizontal velocity. That is represented from this black contour. You can see that there is also some blue dots, but we are not concerned about this because for two reasons. One, because they are out of the front, the stronger flux of the front, and the other one is that they have been deployed later in time. So probably they also have some kind of problem with the synopticity. Okay. So once we trust our horizontal velocity, let's pass to the vertical velocity. And starting from the omega equation applied to the optimal interpolated reconstruction, we can see how the magnitude is quite weak and there is not a clear pattern. So the first panel on the left. Instead, what we have been seeing in the lot of meanders of the univariate analysis based on the UCTD data, it propagates even in the vertical velocity. So you can see this strong vertical velocity, but they are due to artifacts. So artificial curvature due to the fact that we miss data during the middle, transects are more or less out of the maximum of the magnitude of the vertical velocity. So these are probably artifacts. Instead, when we use the multivariate analysis, so with the constraint, with QG, but especially with SG, we start to see what we expect from frontal dynamics. It means that in the east you have a downwelling, so negative vertical velocity, where there is the denser water mass, and instead we have an upwelling in the west, where we have the lighter water mass. But this is qualitatively, so let's go to a more straightforward comparison. And so we have two transects where we actually observed downwelling in temperature with a warm water filaments get downwelled. We have been seeing this in the raw UCTD data. And so the top panel represents the temperature, but the black contour represents the vertical velocity. So the continuous line is the positive vertical velocity, and instead the dashed line are the negative vertical velocity. And you can see how the FG agree much better with the downwelling, especially in the upstream cast. Well, instead the QG is missing this downwelling, especially for the upstream cast, yes. And another interesting things to note is that the positive vertical velocity coincide with areas where the isopycnal are uplifted. And this is interesting because the further analysis that we've been doing is the Along-Isopycnal one. And so we have been computing, according to what suggests a paper of Mara and Freilich, we've been computing the ratio between the horizontal gradients of buoyancy and the vertical gradients of buoyancy. And this should gives us this first plot in the left. I hope you can see it good. And it's important because this ratio gives an idea to when the uplift component dominates in vertical velocity, and or instead when the along-isopycnal component dominates. So we can see how in the front area the isopycnal component is the one that dominates. And you can see in the B plot the total vertical velocity of SG from SG. This along-isopycnal velocity it's stronger exactly in the same place where also SG is giving us the strongest magnitude. And finally, this last plot, it's a constant density surface where we mapped the salinity. So the salinity in a constant density surface acts like a tracer, and so it's giving us the information that the water mass it's actually crossing some depth, that you can see the contour there, and it's getting down, moved by the divergent component that you see in the arrow, I hope so. And it's getting down and proceed along the isopycnal towards the eddy center. So to have a further estimation of what's going on in this eddy, we've been doing 3D advection of virtual particles. And in particular, I've been doing this starting from the CTD cast position. I didn't mention that probably but you also saw in this map. So the green stars are the CTD upstream cast, and the reds are the downstream CTD cast. You can also see it in this 3D plot in the upper part. And so we've been advecting particles below the mixed layer, and we observed how they, based on their position in the front, they get subdued or they get back in the mixed layer. So there are two examples, the C and the D panel. And in particular, the interesting one is the D panel, because the particles get subdued, get unwelled, and comparing the position where these particles ends, we can see an agreement also with the nutrients concentration of that we see in the CTD cast. So this is particularly interesting. And that's more or less all. Let me summarize with some conclusion. The variational analysis provided us a physically based way to combine different observations. In our case, they were UCTD and ADCP, but this approach can be developed, can be furtherly developed for to use other kind of observation, like maybe the one that comes from the upcoming satellites SWOT or Argo floats. So this is an approach that should be considered always more. And then with our reconstruction, we estimate for the first time the Along-Isopycnal component, at least for what we know. The previous studies that we have been doing this are based on models. Instead, we have been using observation in our case. And so we observed how the Along-Isopycnal component dominates in the frontal area. And this suggests us that we've been observing a submesoscale features. And we obtained that the Semi-Geostrophy is the better framework to account for this stronger vertical velocity. And in particular, we observe values of 30 meters per day that even agree with subduction evidence. So as we saw, the temperature filaments and the nutrients. And yeah, exactly. So the last point is concerning that the nutrients, the biogeochemical trace that we have been sampling with the CTD, and that agrees with the displacement of our virtual particles in our fields. And that's really all. So thanks for the attention. And if you have any questions, I'm here.
Thank you very much, Eugenio. So is there any question for Eugenio? You can ask also in Spanish or English, whatever you prefer. So please go ahead. Who wants to start? And we can have a discussion. It seems that from YouTube, the chat is not on, is not activated. So
yeah, I forgot. I can turn it on right now.
Okay, but in the meantime, any question from the people who are in Zoom?
Yeah. No, just let me check. I'm gonna habilitate the chat if I know how to do it. Okay, I don't know how to do it.
Okay, maybe I can start with a comment on the patterns of vertical velocities with the different methods are quite different. No? Well, you already explained it a little bit, but it's true that when you see it at the first time, it's like quite surprising to see these big differences. Can you comment on that, or
yes?
The question always is how we can be sure that the method Semi-Geostrophy. It's true that you have indirect evidences with the from CTD, with the subduction that you see from the CTD transects and so on, but maybe you can develop a little bit further to convince the audience.
Yes. Until now, we can just, I'll try to do some qualitative estimation, firstly on the horizontal velocity with the skill score, and then okay, yeah, we have some agreement with the evidence. To be 100% sure, we should be some model test. Okay, so once we have the total vertical velocity from a model, we can try and test these methods on the complete field and then see what we observe with SG, QG, and even different strategy of sampling and reconstruction. So basically doing an observation system simulation experiment. But even if we didn't do that, we just rely on observation. Now in this plot is not too clear, but there was another one not included in this presentation where you can see the transect of the boat, and so you can see how these shapes.
We are not seeing your screen, Eugenia. I don't know if you want to show
sorry,
something. Yeah.
I forgot. Okay, so this was the plot that you were referring, and in particular, the B panel shows really strong vertical velocity, but they are now what is missing in this plot is the boat transect. So you will see. You could see if we add the boat transect that this maximum are out of the sampling area. So this is the most. It's quite relevant because it means that the gradients used for the computation of this vertical velocity are fake because we don't have information in here. This is the problem. And yeah, also then the drifters, even the drifter, you can see this line, this contour here is the dynamic height. So in theory, if this was true, this were true, the drifter should follow this particular curvature. Instead, they didn't. Instead, they followed a quite straight path. So this is a further evidence of the fact that this is just this meandering is just an artifact.
Okay, thank you. So more questions for Eugenio?
Eugenio?
Yes?
This is Simon. I just was thinking that maybe some people is wondering about the potential contamination of your vertical velocity results due to waves, internal waves, or components. Maybe at least you can comment that you are aware of that and you.
Yeah. I just mentioned that. Yeah, I just mentioned this problem in the beginning. Because since we are in a region where the phenomena are quite overlapped. Yeah, this slide you can see. But yeah, we have been doing, especially because we have been worried about that using the divergent component of the ADCP, that it was extracted from Helmholtz decomposition. We were worried that this component can be just an artifact of the fact that we've been sampling maybe in an inertial time. We have been sampling an area that is also affected by tides, but to estimate if this was a problem, I mean, there is a part of the work that is still ongoing, but we've been checking with a barotropic model the signals of the tides here in the area, and we saw that the phase are quite similar, and the magnitude they are pretty small. So since we observe a magnitude of 0.3 meters per second of the divergent component, we can be confident that these are real divergent components. They are not based on the inertial signal. And this is like a point for the future work. To be 100% sure, it would be nice to have moorings in the same area, so we can resolve the temporal and spatial variability and remove the inertial components. For sure, our signal is contaminated, but the idea is that the magnitude are small, so not too relevant.
Okay, thank you.
Eugenio, here, Barbara. I have a question about the vertical velocities, the figure that you showed before.
Yes. Ooh. Yeah.
Yes, this one. Okay, because in the objective analysis or optimal interpolation, you have two correlation scales that allow you to smooth the original field in 2 dimensions. So you can know that you don't have, I mean, you are smoothing in the same way in both axes. But and in this new method, how do you work with this?
Okay,
with the smoothing. I mean.
It's a little bit technical, but the correlation scale are the same, but the way in which they are treated in a mathematical way, it's a little bit different. In an optimal interpolation, you assume that your information is spread through the domain with a Gaussian, and so the correlation length it's actually the half width, half maximum of this Gaussian. And instead, in the variational analysis, they enters in this in the formula, in the cost function. So it's a little bit tricky to enter in the detail, but in the end, the correlation scale that I've been using are the same, and they have been estimated. I didn't include the slide for this, but they have been estimated with empirical correlation of the dristers of the UCT data, and then also using cross-validation method. It means that we remove part of the observation and we check what correlation length minimize the RMSD between the this test data set not included in the analysis and the analysis. And at any case, I can tell you that both OI and variational analysis use 35 for the horizontal scale and 15 for the, 15 kilometers for the horizontal scales and 35 for the vertical ones, especially because the transects were separated by 17 kilometers. So,
yes, but for what I see is that you use the same correlation scales, but they are applied differently. So they smooth the original field in a different way.
Yes, yes.
And my concern was about, because yes, you to infer vertical velocities, you are using finite differences. So if you have too much gradients between with the same grid resolution, if you have too much gradients, you are introducing more error to the inference of the vertical velocity. So maybe a way to, I mean, I think it will be good to have like an estimation of the error of each one of these vertical velocities to know that. Yes, because in the second plot you say that this is unreal, no? These extreme minimum values. Maybe if you infer some kind of error, you can say, okay, here the error is too big.
No, actually, I have the errors. I didn't have it here, and actually, I didn't. Maybe I have some plots somewhere, but yeah, no. Both of the methods provide you an error, and the error is based on the fact that how far you are from the real observation. So, as I told you before, this strong vertical velocity, it's in an area where we don't actually have observation. So if we looked at the map of the errors, we can see that the errors of the density is stronger here. And then I didn't do this. The next step that will be to propagate the errors on the density to the formula, and then you can have also an estimation of the vertical velocity. But I can tell you that in any case that the density error here, it's bigger. It's quite big. And yeah, also the optimal interpolation gives you, both methods gives you an idea of the errors. I didn't do the part of propagation, but at least I have an idea of.
This point raised by Barbara about the errors is interesting. What you have is the errors for the density field, no? Because of the vertical velocities, it's a derived variable, so you should derive it, no? Or
you should just propagate the formula, and then you can have it.
But also include the errors associated with the calculation, because you are using finite differences in the QU omega equation that have higher gradients. So this can, I mean, the errors can be propagated and because you are derivating 2 times. So I think, yes, I think that the point here is to be careful about the gradients that you have in the original data, and how they can introduce errors to the vertical velocity.
Yeah, definitely. Yeah, that's the problem with the omega equation, that when you can't reconstruct the gradients well, and you use the omega equation, that you have the second derivatives, as you said, all the errors explode. So yeah, maybe actually I didn't see paper where they did this error propagation, probably because it's quite complex when you have.
Yes, it's quite complex. You can check the paper of Enrique Payat-Sanz, two papers in which I think they, at least in one, he infers the error in. I think he has two ways of infer the error, but sure, it's not easy, and you have to make assumptions and all this. But maybe you can check.
Okay, yeah, no, definitely. Thanks.
To see if they can help you to.
Yeah, interesting.
Okay, thank you, Eugenio. Good talk.
Any other comments or questions?
Hey, this is Baptiste.
Hi.
Can you hear me? Yeah. No, just to say congratulations, Eugenio. Thank you for this talk. And just to follow on with what you said before, so do you plan to use models to confirm these results? And
yeah, I can tell you when, but I will really, and also some comments from the US people suggest that it would be really nice to test this reconstruction method with models, and in this way, also according to what Barbara said, we can actually estimate the errors, because in the end, it's the only way to have some kind of idea of how good our method reconstruct the field, and then how good we can estimate the vertical velocity. So yes, we plan to use this, and in particular WMOP, and maybe something with some model, the process study ocean model. I don't know when, but hopefully soon.
Yeah. CALYPSO is a perfect opportunity for this.
Yeah.
That we have these models,
No, that's definitely
sufficiently realistic to do that.
Sorry, what?
We have these models that are high resolution.
Yes.
Also sufficiently realistic to evaluate.
No, definitely, yeah. Now we have to schedule a little bit the agenda of work, but it's definitely on it.
Okay.
Yes, it's part of the plans, but it's true that this study is so detailed and so complex also that it's taking longer than expected, but at the same time we are all learning a lot. But hopefully really now it's almost the end, well, at least for the submission, no, Eugenio? And so new topics can be developed further. Anyone else? No?
I don't know how I can enable the questions from YouTube, but
well, don't worry. That's okay.
Yeah.
So I think I cannot see anyone else. No. Okay, so thank you very much, Eugenio, and also all the audience, and so see you at next seminar. Bye.
Bye.